This video contains the solution to free response question number 3 from the 2009 AP Calculus BC exam, Form B. And in this problem, given a graph that looks like this, and this is with calculator, it's a number 3. Continuous function f is defined on the closed interval from -4 to 6. The graph consists of a line segment and a curve that is tangent to the x-axis at x equals 3. And on the interval 0 to 6, the curve is twice differentiable with f prime of x is greater than 0, so it's concave up here. It certainly looks like that. So is f differentiable at x equals 0? Use the definition of the derivative with one-sided limits to justify your answer. This is a graph of f. So is f differentiable there? Well, what do you think? It is not differentiable there because you cannot take the derivative at a sharp corner. Now, I'm going to make sure that we know what we're talking about. They are talking about the function f, and that is the function f. Okay? So let's be clear about that. Is it differentiable at x equals 0? No. And then they want us to use the definition with one-sided limits to justify your answer. You would say this, that the limit as x approaches 0 from the negative side here of f prime of x. Oops, sorry, that's not what we want to write there. We want to write the definition of the derivative. So we want to write f of x plus h minus f of x over h, and this should be h approaching 0 from the negative side. So as we have little tiny negative h's here, this is the definition of the derivative. We want to say, well, that's a slope, right? That's the slope of this, which we could actually say if we wanted to. Actually, we don't have a point there, so it doesn't matter, but it's some positive number. And on the other side, the limit as h approaches 0 from the positive side of the same expression, that would give us the slope coming in from the other side, and that's clearly a negative slope there. That's equal to some negative number. So the limit as h approaches 0 without a side does not exist. Okay, part B, for how many values of a in between -4 and 6, let's see, including -4 but not including 6, is the average rate of change of f on the interval from a to 6 equal to 0? And then give a reason for your answer. Well, let's see. Average rate of change is the slope of a secant line. So we're talking about slopes of secant lines between, for some x value, and 6. So if we want the slope of a secant line to be equal to 0, I think we're talking about this secant line and this secant line. Because at this point, if you connect to 6, the 6 is fixed. We can't move that. We can fix what a is. So from here to here would give us a 0, and from here to here would give us a 0. So it looks like there are 2 of them. So for part B, 2 values. And give a reason for your answer. Well, I guess we could say, let's see, the line y equals 1, right? I mean, this is the y coordinate of 1. In intersects f twice, and that's of course not including that point, not including the point at 6, 1. So two secant lines with slope of 0, something like that. Let's see, part C. Is there a value in between -4 and 6 for which the mean value theorem applied to the interval a through 6 guarantees a value c? Let's see, c between a and 6. So we're picking a somewhere in between -4 and 6, and then a c in between whatever we pick in 6, at which f prime of c is equal to 1/3. Well, okay, so we want to find some point where the slope of the secant line, remember the mean value theorem says average slope or slope of secant line equals instantaneous slope or slope of tangent line. So we want to find one where the slope is 1/3, and they're fixing this point, right? So let's see, if we draw a line with the slope of 1/3, actually that looks like it would go through here. So let's see, is there a value for which the mean value theorem applied to this interval guarantees a value of c for which f prime of c equals 1/3? There is. The value of a, in other words, the point we'd have to pick here, would be 3, because that is the value that would give the average slope of 1/3, right? Because this is the point 3, 0, this is the point 6, 1, rise over run would be 1/3. And where is the point C? Well, it's somewhere in here, right, where the tangent line's parallel to the secant line. Where is it exactly? That's not what they're asking for. They're asking for where the A is, right? Where we'd have to set that. So we would say, yes, at A equals 3. And we would say, because the slope of the secant line is 1/3. And if you wanted to show the justification for that, the math would be 6 minus, let's see what we have, 6 minus the x-coordinate here is 3 over, oops, sorry, x-coordinates, rise over run, y minus, so y minus y over x minus x is equal to 1/3. And then part D, the function g is defined, okay, so we've got a function g, this is a function defined in terms of an integral, the area under this. The first thing we should think here is that means that g prime of x is equal to f of x. Okay, one of the first things we need to realize here. When we have a function defined in terms of an integral, the derivative of this is equal to this. If there was anything funny going on up here, we'd have to multiply by the derivative of what's inside, but it's just an x. So on what intervals contained in this is the graph of g concave up? Explain your reasoning. Well, we have part of the reasoning done already. We know that the derivative of the g function is f of x. And that means the second derivative would be the slope of this. So we're looking for where g is concave up. So g is concave up when the second derivative of g, its concavity, is positive. So this is positive when the derivative of f is positive, and that means when f is increasing. So let's see, f is increasing from -4 to 0 and from 3 to 6. So from -4 to 0 and from, what else did we say, and from 3 to 6 it's also increasing to 6, right? Again, we said the second derivative here is the same as the first derivative of the f function, so when this is increasing, when f is increasing, this is positive, and so that means that's positive, and that's the g being concave up.